Okay, so the last topic we're going to talk about with regards to the Diels-Alder reaction is Diels-Alder stereochemistry. Right? So we've said that we can put all kinds of groups onto our diene or our dienophile. But of course, you might ask the question, so if I have a trans double bond or a double bond where the two groups are on opposite sides, does that give me the same product as cis double bond? Right? What if these two groups are on the same side? And it turns out that you get more or less the same product, but you get diastereomers of each other, you get different stereochemistry. And so uh, a Diels-Alder reaction, there are no intermediate carbocations. The Diels-Alder mechanism is very, very easy because it's always the same three arrows and it's always a single step, right? We don't need any reaction conditions for these. You can just heat these up and away it goes, right? And so all the Diels-Alder reactions that we've seen in the previous couple of videos have all just had no reagents, just kind of adding energy to the system. Right? And so the mechanism is always going to be the same. Arrow 1 goes to the dienophile, arrow 2 comes back to the diene, and arrow 3 moves things over. Right? Arrow 1 goes to the dienophile, arrow 2 comes back to the diene, arrow 3 moves the pi bond over. Right? And so in both cases, we're going to get 6-membered ring with a pi bond in it. Right? If you want to go through, right, the carbons 1, 2, 3, and 4 are over here. 1, 2, 3, 4. We don't have anything else to add to those, but carbons A and B both have isopropyl groups on them. So we're going to put an isopropyl group there and an isopropyl group there. And we're going to get the same thing here. But because all of these reactions happen, or all of these arrows, excuse me, happen in a single step with no intermediates, this is a concerted reaction, right? Concerted single step mechanism, which is really just three ways of saying the same thing, right? Saying single step, saying concerted, saying no intermediates, all of these mean the same thing, right? We go from starting material to product, we don't have any carbocations or anything else in the mechanism. But practically what this means for us is that the stereochemistry of the starting material determines the stereochemistry of the product. Because there's no time, there's no intermediate where those kinds of things will change as we go through this. So in this case, when we start with the isopropyl groups opposite each other, right, we have a trans double bond over here, we're going to get the anti-relationship between these two isopropyl groups in the product. Right? So we get the trans double bond, we get the anti-relationship in the product. If we have a cis double bond, right, or Z if you're into German, right, with the Z double bond here, we get these groups in the final product will also be syn to each other, right? So depending on how the double bond looks, right? So again, the isopropyl groups are opposite each other in the first example, they end up opposite each other in stereochemistry in the product. If they're cis to each other, if they're on the same side in the starting material, they're going to be cis to each other in the product. This is very much like the epoxides, right? The stereochemistry of making an epoxide. If we look at the double bond, how the double bond is in the starting material is going to match how the wedges and dashes are in the product. And so the stereochemistry of the dienophile, right, will always work this way, right? If we have a trans alkene, you'll always get the anti-product. If you have a cis alkene, you'll always get this syn product. So it's pretty straightforward. This is basically the same thing that we talked about with epoxides. When you use MCPBA on an alkene, we're following the same rules, right? Things that are on the same side tend to stay on the same side. Things that are opposite tend to be opposite. We also have the potential for stereochemistry on the diene, right? So if I have a diene that looks like this, right? I'm going to draw in the hydrogens just to kind of show how this works. And I'm just going to use a very simple double bond. I'm not going to add anything else to the dienophile because we're only going to focus on one thing at a time. When we do this Diels-Alder reaction with this particular diene, right, 4 pi electrons here, this is our diene. The mechanism is the same. We add to the dienophile adds back in, we move the pi bond over, we make a 6-membered ring. In this case, you're going to get opposite stereochemistry, right? The two methyl groups will end up opposite each other. If you change one of those methyl groups, then of course you're going to change the stereochemistry of the final product. Right? Add to the dienophile, the dienophile adds back in, we move the pi bond over, make a 6-membered ring. In this case, you get both of them with the same stereochemistry. Right? So on a diene, it turns out that it's not quite as easy to kind of intuitively figure this out. But basically you have two positions that are kind of inside the mouth of the diene, if you want to call that. Right? And then you have two positions, I want to make these triangles, right? These two are outside, kind of the mouth of the diene. If you imagine the diene as a mouth, right? These are inside it, these are outside it. Inside groups will have the same stereochemistry. In the product. And outside groups will also have the same stereo, right? So in this case, in our first case, with the methyl group and the hydrogen are the two inside groups. And so because those two are inside, those are going to both have the same stereochemistry. The methyl group and this hydrogen are both dashed, right? This methyl group and this hydrogen, so these are the outside groups, triangle group, that's almost a triangle, right? Those two are also going to have the same stereochemistry, so one is wedged, and then the other one, if I drew it in, would be wedged on the bottom carbon as well, right? In this case, both methyl groups are the outside groups, and so they are going to have the same stereochemistry here. There are also two hydrogens that aren't drawn. Those would be the inside groups, and they, of course, will have the same stereochemistry there. This is especially important if we use something like cyclopentadiene, where we have a ring that is a 4 pi electron conjugated system that acts as a diene, right? Cyclopentadiene is non-aromatic because it's got a neutral sp3 carbon in it, so it's still reactive, and we can react this with whatever, right? I'm just going to keep with our simplest thing here. So this pi bond comes and reacts with the dienophile. The dienophile adds its electrons back in, and we move those electrons over. Now we're going to have a 6-membered ring. It's going to have a pi bond. Now this is carbon 2, carbon 3, carbon 1, and carbon 4, right? double bond is between carbons 2 and 3. But then what we have is we have this CH2 group, this neutral sp3 carbon that's halfway between carbons 1 and 4. Now that neutral sp3 carbon is the inside group for both of them. And so what you're going to have is you're going to have kind of going up from both carbons 1 and carbon 4 is that CH2 group kind of halfway in between them. So drawing it flat like this, it kind of looks weird. You can also draw this if you're feeling particularly artistic. You can draw it like this, where here's carbon 2, here's carbon 3, right? Between carbons 1 and 4 is this kind of neutral CH2 group that is up from both of them, right? And then here would be A and B. Okay. So we can have stereochemistry on the dienophile, which is pretty straightforward because it's just like the epoxide stuff that we did. Trans double bonds give anti relationships in stereochemistry. Cis double bonds give syn relationship in stereochemistry. A little bit more complicated is stereochemistry on the diene itself, because then you have to worry about kind of inside groups and outside groups, right? Inside groups will always match each other in stereochemistry, and the two outside groups will always match each other with stereochemistry. But one inside group and one outside group will always be opposite each other.